Okay, so up until now, we've just been looking at just one equation of the, let me, if I go right back. So this equation here, I said to you, was an equation in two variables, x and y, and it's a linear equation because it's x to the power 1, y to the power 1. So this is a linear equation in two variables. And up until now, we've just been looking at the one equation, and we said there's an infinite number of values of x and y that satisfy that, and when I graph it, I get a line. So what we're going to do now is look at a slightly more complicated case and imagine that we actually have a set of two of these sorts of equations. So here I've got two linear equations in two variables. What we want to do is we want to look for values of x and y that satisfy both equations. So what we say is we want to look for values of x and y that satisfy these equations simultaneously. That's the maths jargon, if you like. So when we have a set of two linear equations, we look for values of x and y that satisfy both of these. So let's look at this geometrically first, and then we'll come back and look at it algebraically. So if I were looking just at the first equation there, y is equal to 3x plus 2, we would say to ourselves, look, that's a linear equation in two variables, therefore there's an infinite number of points that satisfy. When I graph them, I get a line. And hopefully I've drawn that over here. So here is the set of points that satisfy y is equal to 3x plus 2. For whenever I choose an x value, the y value here, 3 times 2 is 6, 6 plus 2 is 8. Right, so this is a graphical representation of all the values of x and y that satisfy that. Likewise, that's a graphical representation of all the x and y values that satisfy this equation. You can see that there is just one point there that is in common, the point 1, 5. So what that would say to us is that when x is equal to 1 and y is equal to 5, I should satisfy both that equation and that equation. Let's go back and check. So, when x is equal to 1 and y is equal to 5, let's look at this equation. Y is equal to 3x plus 2. Is it satisfied? On the left-hand side, is y, so that's just 5. On the right-hand side, it is 3 times 1 plus 2, which is also 5. So that satisfies the first equation. That's good. Let's check the second equation. It is y is equal to minus 2x plus 7. So the left-hand side again is just y, so that's 5. And the right-hand side is minus 2 times 1, which is minus 2. Minus 2 plus 7 is indeed 5. So in fact, 1, 5 satisfies both of these equations simultaneously. So the task we're going to set ourselves is, given these equations, how do I find these two values here? How do I solve these simultaneously? I mean, I guess one thing I could do is draw the picture. Now, in this case, I drew the picture, and I could quite happily read off, or well, I guessed anyway, didn't I? I guessed that that value was 5 there. But quite often you will have trouble trying to guess what those values are, even if you could draw the graphs. So what we do now is we use our abundant algebra skills to help us out. Okay? The other thing to look at here is, look, these things are straight lines. So there's no way this thing's going to come around here and intersect again. Right? So in the main, we are expecting just one solution. Right? Now, it's possible that I might not get any solutions if those things are parallel. But I'm not expecting 2 answers or 3 answers. I'm only expecting one. Okay? All right, let's see how we go. So, solve the following equations simultaneously, it says. So, for the sake of explaining what I'm doing, let me number these equations. So let me call the first one equation 1 and the second one equation 2. And I notice in the notes it actually gives names to different methods. So let me go through them. I mean, I'm not overly worried about what method you use where. They're essentially the same thing. So as far as I'm concerned, solve the simultaneous, get the answer, okay, is what I'm after. I doubt very much that I would say solve this using this particular method, because that's not very important as far as I can tell. So, but anyway, the first method that the notes have is called the substitution method in there. So let me just highlight it so that you can pick that up as being something that you will read about. I think even the exercises might say solve something via the substitution method. But as I say, you won't get that in the assessment. I'll just say solve the silly thing. And in fact, to be perfectly honest, in a quiz you'll probably get a question like solve simultaneously. But given that the mid-semester and the final are multiple choice exams, if it was multiple choice and I say, oh, is this the solution? Well, you wouldn't have to solve the silly things. You'll just go along and check. Right? So I can't even ask that as a question in multiple choice. So in the multiple choice, what I will do, I can tell you now, is I'll say, here's a set of simultaneous equations. The x value is. Right? And I'll give you a lot of different possibilities for the x value, so that you can't just simply substitute in and work out which one's the answer. Okay? That's just one of the difficulties we have by having a multiple choice format in there. Or I could also say the y value, but you know, I can't give you the full solution in a multiple choice exam. But anyway, here we go. Let's use the substitution. I jumped miles ahead there. So here we go. So in the substitution method, the first step, I think, if I can label them, is to make one variable the subject of one of the equations. So that's pretty vague. So it doesn't matter whether you make x the subject or whether you make y the subject. And it also doesn't matter whether you use equation 1 or equation 2. Just do it with one of them. Now, in this case, the obvious choice is to make y the subject of equation 1, because the y has a coefficient of -1. Right? So I don't have to do any divisions or anything. So I can say here, from equation 1, I'm going to say y is equal to 2x plus 3. So I've made y the subject. That's the first step.
Sorry, isn't it -2x?
If I take the y over to there and bring the 3 over to there. Yep. Okay, so let me call that equation 3. So equation 3 comes from equation 1. The second step, step 2, will be to substitute this So to substitute the equation that you just got into the equation you didn't use. So equation 3 came from equation 1. So therefore I'm going to substitute equation 3 into equation 2. Okay, so here, put equation 3 in to equation 2 in there. And I have 4x plus 5. Now, y is 2x plus 3. So I'm going to put that for everywhere I see y equal to 1. So what this is saying, of course, is on this line, if I choose a value for x, that's the associated value for y. That's what it's telling me. And so I'm saying, what of those points actually might satisfy this equation here? And so now I have a linear equation of one variable, and I can solve that for x just by making x the subject. So solve this for x, and I will get 4x plus 10x is 14x, plus 15 is equal to 1. Subtract the 15, so I've got 14x is equal to minus 14, so x is equal to minus 1. So I should say substitute this into the other equation, and I guess and solve. I'll put into step 2 there. So let me call this result here equation 4. And I can put that back into any of the equations I've got, but the obvious one to put it back into is this one here, because I've got y in terms of x. So the obvious spot to put this result is back into equation 3, sitting there. So step 3 says substitute the result into, now I'll say a previous equation, but I really mean equation 3. So let me grab a spare piece of paper here. So in here, i.e., I'm going to put equation 4 into equation 3. And I will have y is equal to 2 times minus 1 plus 3. That gives me minus 2 plus 3, that is equal to plus 1. And so I believe my solution is x is equal to minus 1, y is equal to plus 1. So therefore, solution is x is equal to minus 1, y is equal to plus 1. Oops, can't even see that. Now, the beauty of this is that I can tell whether I got it right or not. So I'll just say here, can check my answer. By going back to my original set of equations, I can just see them up there. I can check my answer by just going back and having a look. Let's go up here. 2 times minus 1 is minus 2. Minus 2 minus 1 is indeed minus 3. So minus 1 works in that equation. Let's go here. 4 times minus 1 is minus 4. 4 plus 5 is indeed 1. So I checked my answer, it worked, and I'm happy. So that's my algebraic solution in there. I say it's the values of x and y that have satisfied those two equations. Geometrically, I can say geometrically, if you can read that. So I'll say geometrically, This is the point of intersection of the two lines. So those two lines intersect at the point minus 1, 1. We're solving simultaneous equations, and I said, look, here's one method. It's called the substitution method, where you make one variable the subject, substitute it in. Let's do another one and use the other method. And so in this case, I'm going to use what's called the elimination method. And as I say, I don't really care which method you use. I interchange all the time. I do whichever's simpler. But they're equivalent, so it doesn't really matter. So using the elimination method. So it's probably actually a good idea to begin by writing your equations in an, I'd say, a simpler form. So here, this is not part of the elimination method, so let me just do it up here. I could write that if I multiplied everything by 2 here, I'd have 4x, and then I'd have minus 5y is equal to 2. So I've multiplied by 2, I've got 4x is equal to 2 plus 5y, and then I've brought the 5 over. Okay, so I've just rearranged that to that. Likewise here, I would write this as 13x minus 5y is equal to 6. And then I would call that equation 1 and equation 2. So I would write the equations with the variables on the left-hand side and the constants on the right-hand side. I'd do that as a first step, whether I was doing elimination or substitution. Now, my first step. It's rather long to explain, easy to do. So what I want to do is I want to multiply the equations, each equation, by a constant. It doesn't have to be the same constant with both equations, but I want to multiply equation 1 by a constant and multiply equation 2 by a constant, so that I've got one of the variables having the same coefficient in both equations. It could be the x variable, it could be the y variable. Now in this case, that step doesn't need to be done, because as it turns out here, I actually have a minus 5 there and a minus 5 there. All right, so I don't have to multiply that by anything to get coefficients to be the same. Okay, but I could have, if I'd wanted to make the x coefficients the same, I would have multiplied this equation by 13 and I would have multiplied this equation by 4. And that way I would have had the x coordinates having the same coefficient. But I don't want to do that because that's too hard, given that I already have the same coefficient with the y's. So I can say here, no need in this case, no need for this in this example. So we're lucky, we didn't have to do step 1 there. So step 2 now says subtract one equation from the other. So that's Sounds a little bit strange. How do I subtract equations? Let me try to explain that. Now, if we were to look at our equations, the way we interpret them, the way we think of an equation is here. Let me look at the first equation. 4x minus 5y is equal to 2. What I'm thinking is the number on the left is equal to the number on the right. Likewise, in this equation, the number there on the left is equal to the number on the right. So if I subtract that number in equation 1 from that, the left-hand side of 1 from the left-hand side of 2, I should get the same as the right-hand side of 1 subtracted from the right-hand side of 2. If that number's equal to that number's equal to that, subtract that from that, subtract that from that, I should get the same result. So I'm going to say subtract equation 2 minus equation 1. And it's going to be, the number on the left-hand side here, it's going to be 13x minus 5y. And then on the right-hand side, I have 4x minus 5y. So I've subtracted the left-hand sides, and that's going to be equal to 6 minus 2. Subtracted the right-hand sides. And given that I have the same coefficient of y sitting here, those two terms are going to eliminate each other, if you like. I'm going to eliminate the y variable from this equation. So when I do it here, I have 13x minus 4x is 9x, minus 5y, minus times a minus is plus, minus 5y plus 5y, they are eliminated. And on the right-hand side, I've got 6 minus 2 is 4. And so that tells me x is equal to 9 divided by 4. So in this case, and quite often the case, the numbers don't have to turn out to be nice whole numbers. Right? So this happens to be 2 1/4. Okay, the numbers, there's nothing that says, the only reason that there be nice numbers is so that the arithmetic's not too hard for you. But conceptually, the numbers can be anything. Oh yeah, thank you. Upside down. 4 9s. Cool. So let me call that equation, what am I up to? That's just equation 3. And so now I've got my x value. I now need to work out my y value. And I can substitute into either of those equations. It won't make any difference. I should get the same answer. So step 3 says substitute into one of the original equations to find the other variable. So let me do that. So here I shall put equation 3 into, and I think this one looks a little nicer, so I'm going to put it into 1. But you could put it into 2. You should get the same answer. And that will say 4 times 4 ninths minus 5y should be equal to 2. So I've got minus 5y is equal to 2 minus 16 on 9. 2 is 18 on 9. 18 on 9 on 16 on 9 will be 2 ninths. So now I divide by minus 5 and I'll have minus 2 on 45. And once again, that's not a nice number, but that's what it should be, I think, I hope. And so I believe my solution is, so the solution is x is equal to 4/9, y is equal to minus 2 on 45. And as always, I can check my answer by going back and substituting in there, but that's way too hard for me. I'm just going to trust that I got that one right, okay? But conceivably, I could check it. So that's my algebraic version of things. In terms of a geometric interpretation, that tells me that that is the point of intersection of the two lines. And so if I were to go back, and I've got myself a little grid here. There we go. I could probably have a go at drawing these lines. So sitting in here, the line 4x minus 5y equal to 2, it's not easy to draw, but it goes something like this. So that would be the line 4x minus 5y is equal to 2. The other line is 13x minus 5y is equal to 6. I've got that around that way. I think this one goes something like this. That would be 13x minus 5y is equal to 6 in there. And here would be your point of intersection, and that will have coordinates 4/9 minus 2 on 45 in there. And so that is an example where being able to just draw the pictures probably wouldn't help you find the actual answer. You really do need to do the algebra in that case to get those numbers. That's supposed to be a comma in there. But let me go back and just summarise a little bit. With the substitution method, I would have made y or x the subject of one of those. In the elimination method, I get the coefficients of one of the variables to be the same. That's essentially the difference between the two methods. As I say, I don't care which method you use. I might put that there. Leave it like that. Okay. So, solve the following system of equations. So the first thing I would do is I would rewrite these equations with the variables on the left and the constants on the right. I find that easier to do. So here I would rewrite. Well, I guess the first thing, let me go back. These, I actually have here two linear equations of two variables. So that tells me I can use my simultaneous equation methods to solve these, to get the answers. So here on the left I will say 5x minus 2y is equal to 4. This one I would write as 10x minus 4y is equal to 1. So 10x minus 4y is equal to 1. And I would call those equation 1 and equation 2. Now, in this case, it's not too hard to make either x or y the subject of one of those equations, but given that they've got a coefficient that's not 1, I think I'm going to do an elimination method. So what I'm going to do is I'm going to multiply equation 1. So I'm going to multiply equation 1 by 2. And you'll see that when I do that, on this side here I have 2 times 5x minus 2y is equal to 2 times 4. And so I have 10x minus 4y is equal to 8. And the important part here is I have my coefficient of y being the same in both equations. Actually, it turns out the coefficient of x is the same as well, but that's neither here nor there. So that's equation 3. So here I'm doing an elimination method, if you like. And now I'm going to say equation 3. Now, this one came from equation 1, so I'm going to subtract equation 2. So equation 3 minus equation 2. And I have 10x minus 4y from equation 3. And from equation 2, I have 10x minus 4y. On the right-hand side, I have 8. And from the equation 2, on the right-hand side, I have 1. Now in here I was actually trying to eliminate the y, but what's happened here is I go 10x minus 10x, that actually cancels out. I've got minus 4y plus 4y, so on the left hand side I end up with 0 in here. And you think to yourself, 0 equal to 7, I can't do that. So the interpretation is, it doesn't matter what value of x and y you choose, you can never make 0 equal to 7. So this says this set of equations has no solution. So I'll write this in here. Clearly, no values of x and y will make this work. Sorry. That's okay, I'm used to it. And that's what it will mean. These two lines are going to be parallel. And if you have a look in here, well, I mean, the obvious thing to do is look here, isn't it? 10x minus 4y. If you make y the subject of that, given that that coefficient and that coefficient are the same, you're going to end up with the same slope. It's going to be 2/5, isn't it? Both of them are going to have slope 2/5. That's right. So clearly no values of x and y will make this work. So that implies no solution. And down here, we'll say the lines are parallel, because I'm going to draw them here. The lines are parallel is our conclusion. So where's our little ruler here? 1/2, 0 minus 2. And the other one goes about here. It's a bit hard to... But they actually look something like that, in fact, in this case. So this line here is 5x minus 2y is equal to 4. This line is 10x minus 4y is equal to 1. And clearly, there is no value of x and y that lies on this line and that line. Okay, so let's do another example. Once again, let me begin by rewriting the equations. So I would rewrite these as 4x plus y is equal to 4 plus 5 is 9. And this one I would write, now I like to put the variables in the same order, so I'd write that as 24x plus 6y is equal to 54. So let me label those, equations 1 and equations 2. This time, the obvious method of solution would be a substitution, because I've got a y here with a coefficient of 1, so it's dead easy to make y the subject of that equation. So I'll say from equation 1, I'm going to use my substitution. It's going to be minus 4x plus 9. So I shall call that equation 3. And I got equation 3 from equation 1, so I now need to substitute it into equation 2. So I will put 3 into equation 2. So I'm substituting in this case. And I have on the left-hand side 24x plus 6, and now I have to substitute minus 4x plus 9. And on the right-hand side I have 54. So I have 24x minus 24x plus 54 is equal to 54. So what I end up with here is 54 has to be equal to 54. And what that says is it doesn't matter what value of x you choose, that's going to be true. So this one has an infinite number of solutions sitting in here. Any value of x will satisfy this. That means the lines are the same, that's correct. And so that says an infinite number of solutions. And our conclusion here are the lines are, now we could say the same, but I'm going to write it like that. I'm going to say the lines are coincident. So this equation, these two equations represent the same line, might be another way of saying it. And of course, if you look at this, I'll go here. If I multiply that first equation by 6, I get 24x plus 6y is equal to 54. You can see they're the same equations. Okay? And so the set of x and y values that satisfy that, of course, all the values that satisfy 4x plus y is equal to 9, or 24x plus 6y is equal to 54. And so that equation passes through 2, 1, passes through 1, it's way up here. Goes like this, something like this it looks like. It's even steeper than that, but anyway. 4x plus y is equal to 9. Every value of x and y on that line will satisfy both equations. So the lines are coincident. Yeah. Yeah. You could have. That's right. It's not risky once you know what you're doing. What I did here was I'm saying the methods that I've showed you will always work. Of course, there are shortcuts if you're wise. Okay? Yeah, that's why it's called a shortcut. That's right. But if you're the mechanical kind and you like to go through the same ritual, do that, and this is what you'll get. Yeah. Yep, for sure. And so, out of all of this, if you've got two straight lines, there are in fact only 3 possibilities. So let me just highlight. So if you've got a system of 2 linear equations in 2 variables, i.e. you have 2 straight lines, they will intersect, be parallel, or be the same. They're the only 3 possibilities. So you're either going to have one point of intersection, they're going to be parallel, or they're the same line. And that's the only possibility. You can never, for example, have 2 solutions. You can never have 3 solutions. You'll either get 0, 1, or infinite.